Premio Nobel, aquí presente, y autoridades del Instituto Politécnico Nacional. Bienvenidos. Muy buenos días. De verdad que estamos de plácemes en el Instituto Politécnico Nacional por contar con un talento de nivel mundial, de talla mundial, y que viene precisamente a brindarnos una conferencia magistral denominada Ondas Gravitacionales, Fusión de Agujeros Negros y Fusión de Estrellas de Neutrones Binarias. Para mí es un privilegio recibirlos a todos ustedes, comunidad de la Escuela Superior de Física y Matemáticas, muy respetados maestros, jóvenes alumnos. Ustedes son la razón de ser de esta gran institución. Antes de dar principio con esta conferencia, tendremos un video que será inmediatamente puesto para todos ustedes, solicitado por George Smoot. Si son tan amables, corre video.
El Centro Universitario de Ciencias Exactas e Ingenierías de la Universidad de Guadalajara se complace en presentar al Dr. George Smoot. Smoot nació en Yukon, Florida, el 20 de febrero de 1945. Es doctor en física por el Instituto Tecnológico de Massachusetts, en Estados Unidos. Su inclinación por el estudio de la creación lo llevó a ser el primer ser humano en asomarse al momento mismo de la generación del universo, ya que sus investigaciones cosmológicas le permiten comprender cómo ocurrió el Big Bang hace más de 13.000 millones de años. La magnitud de este hallazgo lo hizo merecedor en 2006 del Premio Nobel de Física, junto con John C. Mather. Como si fuera un arqueólogo del espacio exterior, con rigor y audacia, participó en diversos equipos de científicos e ingenieros para indagar en los primeros instantes del cosmos, en busca de las arrugas en el tiempo, que nos ha permitido entender cómo y por qué el universo está en expansión. Smoot ha trabajado en instituciones académicas como en la Universidad de California en Berkeley y en el Laboratorio Nacional de Lawrence, Berkeley, de Estados Unidos. Hoy presidente de Physics of the Universe del Polish Center for Cosmological Physics, desde donde se sigue explorando el surgimiento y evolución del universo. Por sus aportaciones ha recibido reconocimientos como el Premio Gruber de Cosmología y las medallas Daniel Challenge, Albert Einstein y una de la Administración Nacional de la Aeronáutica y del Espacio, NASA.
Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait.
I love the show, and it's about the Big Bang, which is what my life work's about. I just had a great time. These guys are so much fun, and the crew works together so well. And the cast, obviously, having a lot of fun.
He's a god to these guys.
Yeah,
you know, they'll travel by any method to any place on Earth to meet a guy like that.
It's bigger than Britney Spears being on How Many Months.
Yeah.
Yeah.
So I'm thinking, you won the Nobel Prize, 3 years ago? So you must deal with a whole lot of what has Smoot done lately. My thought is, we continue my research as a team, Cooper, Smoot, alphabetical, and when we win the Nobel Prize, you'll be back on top.
With all due respect, Dr. Cooper, are you on crack?
Fine, Smoot Cooper. Wow, what a diva.
En el 2018, George Smoot publicó una nueva edición de Arrugas en el Tiempo, libro escrito junto con David Davidson, en el que narra la gesta personal que le permitió alcanzar, en palabras de Steve Hawking, el descubrimiento más importante no solo del siglo XX, sino de todos los tiempos.
If you, like me, you spend day after day studying the universe, you start to understand in a different way. You get used to the time scales, you get used to the huge scales. I mean, it's very hard for people to understand how insignificant man is in the Earth, on the Earth, except now we're starting to have global reach. But how insignificant the Earth is in the solar system, how insignificant the solar system is in the galaxy, how insignificant our galaxy is compared to the billions of galaxies there are.
Bienvenido al CUSEI.
Queremos saludar también a nuestros amigos cibernautas, están viendo a través de XEIPN Televisión, Canal 11, el canal del Instituto Politécnico Nacional, a través de Facebook y de Twitter. Un saludo muy afectuoso. Nos acompaña esta mañana también con la muy digna representación del señor doctor Mario Alberto Rodríguez Casas, director general del Instituto Politécnico Nacional, el doctor José Madrid Flores, coordinador de asesores de la Dirección General del Instituto Politécnico Nacional. Bienvenido, doctor. Y bueno, sin más, ondas gravitacionales, fusión de agujeros negros y fusión de estrellas de neutrones binarias. Y dejo este micrófono para el doctor Miguel Tufiño Velázquez, director de la Escuela Superior de Física y Matemáticas del Instituto Politécnico Nacional. Doctor, si es tan amable.
Buenos días a todos. Bienvenidos a este magno evento. Déjenme comentarles que la visita del profesor Smoot, así como la visita de otros distinguidos conferencistas, como la doctora Jocelyn Bell, que también dio una conferencia magistral en este auditorio, y muchos distinguidos investigadores científicos que nos han visitado desde agosto en la Escuela Superior de Física y Matemáticas. Todo esto ha sido posible gracias a la Cátedra Eugenio Méndez de Ocurro, que instituyó el Politécnico con el propósito de reconocer la obra trascendental del ingeniero Méndez de Ocurro. Y por supuesto, el propósito de la cátedra es fomentar actividades académicas de excelencia, como las que hemos estado llevando a cabo en el curso de este año. Entonces, pues es un gusto, es un honor tener aquí a personalidades como el profesor Smoot. Agradecemos al Instituto Politécnico Nacional que a través de la Cátedra Méndez de Ocurro haya proporcionado los medios para que sean posibles eventos de esta calidad y de este tipo. Entonces, pues bienvenidos todos y continuamos con nuestro programa. Buen día, gracias.
Solicitamos al representante personal del señor doctor Mario Alberto Rodríguez Casas, director general del Instituto Politécnico Nacional, doctor José Madrid Flores, coordinador de asesores de la Dirección General del Instituto Politécnico Nacional, nos brinde su mensaje. Gracias.
Muy buenos días a todas las personas aquí presentes. Es un verdadero privilegio para el Instituto contar con la presencia del profesor George Smoot. Really, it's great for us you present here, Professor, at the National Polytechnical Institute. Dr. Rodriguez Casas apologized because it's not possible for president of the institute to be here, but we are very happy because you are here. El contar con presentadores de la naturaleza del profesor Smoot es extraordinario para el instituto. Este es un trabajo que se ha puesto a cuestas fundamentalmente Miguel Tufiño en su calidad de director de la Escuela Superior de Física y Matemáticas al concebir y realizar una actividad para honrar la memoria de uno de los grandes politécnicos de todos los tiempos, Eugenio Méndez de Ocurro, veracruzano de nacimiento y mexicano y hombre del planeta por definición, creador de grandes instituciones tanto en el país como en el propio instituto, creador de la Escuela de Física y Matemáticas, junto con Víctor Bravo Aguja del Centro de Investigación y Estudios Avanzados, formador de nuestra orquesta sinfónica, del planetario Luis Enrique Erro, en aquel momento en que los computadores mecánicos eran la manera de que teníamos de concebir el universo. Gracias al trabajo del profesor Smoot y del tipo de apoyos tecnológicos que pudo ayudar a desarrollar, nos acercamos prácticamente al inicio del universo, al inicio de Big Bang, y con el universo que se arruga. Él ha sido capaz de describirnos, y lo decíamos en sus palabras, de ver de esos trillones de posibles galaxias cómo han evolucionado y cómo nos encontramos. Seguramente en esta ocasión tendremos acceso a la manera en la cual él concibe el universo y cómo este universo se desarrolla y cómo se va a desarrollar en los próximos 5,000 millones de años que aproximadamente ha de durar. No se apuren, 5,000 millones de años pasan pronto, entonces tendrán oportunidad muchos de ver qué ocurre. Pero estamos seguros que no solamente él, sino la cantidad de personas que alrededor de él han desarrollado, primero, el interés por la ciencia, como los niños, por la astronomía en lo particular y por la astronomía física, será posible que sigamos paso a paso en este apasionante mundo de la investigación, averiguando qué es lo que ha pasado con nuestro universo y hacia dónde va. Profesor, bienvenido al Politécnico. Professor Smoot, you are welcome here. Thank you.
Ya vamos a terminar esta parte protocolaria y vamos a dejar al doctor Miguel Tufiño Velázquez, director de la Escuela Superior de Física y Matemáticas del Instituto Politécnico Nacional, que haga ya la presentación oficial de Mr. George Smoot.
Bien, yo creo que se ha dicho tanto del profesor Smoot que voy a hacer lo más breve posible. George Smoot fue el primer ser humano en asomarse al momento mismo de la creación. No es que haya viajado hacia atrás en el tiempo, sino que sus estudios cosmológicos con globos aerostáticos, aviones espía, antenas en la gélida Antártida, le permitieron comprender cómo ocurrió el Big Bang hace más de 13,000 millones de años. La magnitud de ese hallazgo lo hizo merecedor en 2006 del Premio Nobel de Física junto con John C. Mather. Su trabajo fue tanto teórico como experimental, pues por un lado concibió el modelo y las herramientas matemáticas para detectar la radiación de fondo de microondas, y por el otro desarrolló los instrumentos capaces de detectar el tenue eco de lo ocurrido cuando se formó el universo. Como si fuera un arqueólogo del espacio exterior, con rigor y audacia, participó en diversos equipos de científicos e ingenieros para husmear en los primeros instantes del cosmos, en busca de las arrugas en el tiempo que nos han permitido entender cómo y por qué el universo está en expansión. Smoot ha trabajado en instituciones académicas como la Universidad de California en Berkeley y en el Laboratorio Nacional Lawrence Berkeley de Estados Unidos. Por sus aportaciones ha recibido reconocimientos como el Premio Gruber de Cosmología y las medallas Daniel Chalon, Albert Einstein y una de la Administración Nacional de Aeronáutica y del Espacio, la NASA de los Estados Unidos. Hoy preside el Fondo Physics of the Universe del Paris Center for Cosmological Physics, desde donde sigue explorando cómo surgió y cómo ha evolucionado el universo. Además de publicar en revistas especializadas, se ha dado el tiempo para aparecer interpretándose a sí mismo en la serie The Big Bang Theory, como lo vimos hace un momento. En 2018, Grano de Sal publicó una nueva edición de Arrugas en el Tiempo, libro escrito con Keith Davidson, en el que narra la gesta personal que le permitió alcanzar, en palabras de Stephen Hawking, el descubrimiento más importante del siglo, sino de todos los tiempos. El profesor Smoot viene de la FIL de Guadalajara, donde participó, hizo la presentación de este libro, y por coincidencia este año el libro Arrugas en el Tiempo cumple 25 años de que lo escribió el profesor Smoot, y se ha hecho una nueva edición por la editorial Grano de Sal. George, welcome to Mexico again. I will let you speak now. Please, everybody wants to hear from you. Gracias, bienvenidos todos.
So, buenos días. It's a pleasure for me to be at IPN again. This is the third time I've been here to give a talk. 9 years ago, we were here to use the planetarium to do a world premiere of the show that I learned to be called Cosmologia Maya, but everyone here calls Mayan Skies, which is our English name for it. And so we made the world premiere of that show. I gave a talk for that. We had a big ceremony, and we had the world premiere for that, the most recent time we were here. And so this time, we were brought to Mexico and to IPN because of this book. I'm holding it up so we can advertise it. Because IPN paid money ahead of time to buy some copies, so they probably want to sell them, or whatever it is, to buy some copies to help us guarantee to get this book. Is that correct? So we have to do a little ad for that. and so forth. And that's why there was the video at the beginning that was made for introduction there. We weren't advertising University of Guadalajara. We should have been advertising IPN here, but we didn't have a new video. And we also had a competition among the students at the university to see who could make a video best explaining some concepts. And I recommend that. I'm trying to encourage the students here to make a video to explain something. It's very engaging for the students, and you'll learn a lot. All right, so let me turn, and you have to take notes on the bottom. Let me turn to the topic that I chose to talk about today. And it's designated by this tie. So I bought this tie about the time that Jorge, hold your hand up, Jorge Cervantes and Salvador Galindo and I knew two things. One, that it was coming on the 100th anniversary of general relativity and the 100th anniversary of the prediction there might be gravitational waves. And some of us had heard a rumor from people working on it that they were seeing evidence. And then that was closed up for a while. And so that's what I'm going to talk about today. Right now, and what I have to say is the first two drafts of this paper were in Spanish, because I've done papers with Jorge before, and we've alternated between English and Spanish, but more English, so a Spanish term. But then the magazine Universe offered to publish for free. So if we do English, so we did English. And we now are supposedly working on another history paper on the history of gravitational lenses, which actually goes much earlier than Einstein, but really came into being with general relativity and with the measurements that came after that. But what I want to talk about is a particular part of Einstein's legacy, and this is special relativity by, I couldn't find a good general relativity tie that I really liked, which was the prediction of gravity waves, and then 100 years later, finally, the discovery of gravitational waves. And the amazing thing, it was from emerging massive black holes, massive stellar-sized black holes, and then much more recently, there have been merging binary neutron stars. And if you want to know the history of this, which is very varied, that article that the three of us wrote tell you a lot about the early stages. There was a lot of controversy for the first 40 years as to whether gravity waves were actual real things or artifacts of the equations of what's going on. And Einstein himself, with a postdoc, wrote an article that he submitted saying there were no gravity waves, even though he had earlier said there might be gravity waves. And the referee said, no, you made a mistake, and sent it back. And Einstein got very upset at the journal, never submitted a paper to them again, and said, I never gave you permission to give it to a referee. But it turns out the referee was correct. And later on, the new postdoc that came in talked to H.P. Robertson, who was the referee, and eventually convinced Einstein of the error and fixed it. But you can read more details about that and more of the historical thing, but it still wasn't a solved problem for nearly 40 years. But things have changed. This has become a hot topic in science these days, and it started almost 2 years ago, not quite. But as of last year, a year ago, these three gentlemen were given the Nobel Prize, and there is a reason they happened to get it very quickly. They got it essentially a little over a year after the discovery was announced, and there were some confirmation measurements that followed up. That's very unusual. Typical time scale for the Nobel Prize is 10 years. But as you will see, they have been working on LIGO for 40 years. They're getting older. If you work on anything for 40 years after your PhD, you're not going to be young. And so if they're going to enjoy the Nobel Prize, they have to get it now rather than 10 years from now. And they'll enjoy it more. And we'll see. And so we'll talk about Ray Weiss, who is a professor at MIT, and his interaction with the people from Caltech. He had one of the original ideas, and with Kip Thorne, raised the possibility, and then he had to keep up. he produced the ideas for what became LIGO. And Barry Barish was called in to resolve certain problems that came up. And he understood how to turn it into a real project that would develop and increase over time and eventually go forward. And I'll talk about that briefly. Okay, so though they saw the event in mid-September of 2015, they did not make the announcement until February of 2016, not so long before our paper was getting ready to be submitted, a draft of it to the journal. But as I said, we heard rumors about this beforehand. And here's the important thing. There were two operating detectors at the time this came on. One, H1, up in the right-hand corner, up in the left-hand corner of the United States in Hanford, Washington, with the L-shaped in that direction, and down below in Livingston, Louisiana, with the L-shaped in the flipped over direction. Those were the two detectors that were on and operating, and the light travel time between them is 10,000th of a second, right? So 0.01 seconds, a hundredth of a second. And that becomes important because it actually lets us tell what the speed of light was in the very first event. And you see the first event from Hanford, funny waveform, and then the best fit numerical model, then the Livingston data, the actual waveform, and the numerical simulation, and then the Hanford data. I think which one is flipped over? The Hanford data flipped over because it flipped over and shifted 0.7 milliseconds to line up, to sequence A lined up. Now, it took 100 years to get a waveform that looked this bad. Okay? But this is actually a strong signal compared to whatever it is. But still, it's not pretty like we would have expected if you got to work on something for 100 years. Okay, so let's talk about it. Uh-oh, it's not showing it. We need less light. Those two black things that you don't see are the black holes. They're orbiting around each other. They're distorting space-time. If we could have a spotlights down, it would help. Okay. And they make a ripple in space-time, goes out spherically, and it's distorting space-time, and if you're looking through it, you'll see things move a little bit. But eventually, this is going to come to Mexico. See? And the wave comes by, and it starts distorting the Earth. Stretches it in one direction, compresses in the other alternately. This effect is greatly exaggerated. For a 4-kilometer distance, the change in length was 1,000th the size of a proton, approximately. Okay, so very small effect, so it's very exchanged. But this event actually happened not during the scheduled data taking, but a few days before data taking was scheduled. But everybody had gone home for the day. It was like after 2 o'clock in the morning. People had left at 1. They left the detector running, as you would expect them to, during the engineering runs. And this event came in, and the automatic software sent a telegram, and the person on duty was a young postdoc in Germany, and he got the telegram. So did other people when they email telegram. Woke up in the morning, they found it, but he got to see it. And this is a massive event. The strain, the change in length over the length, is 10 to the minus 21, incredibly small, right? But the masses of these two things were very large. That's the thing that bothered me right from the beginning. 36 solar masses and 29 solar masses going to 62 solar masses, and 3 solar masses worth of energy in gravity waves. The event took place 1.3 billion years ago. It just showed up now because it took the gravity wave 1.3 billion years to get to us. Right? So it took place 1.3 billion years ago. The gravity wave was traveling across all that distance and finally shook up Mexico and the Earth. At that time, on September 14th in 2015, and it got the name Gravity Wave 150914, right? Very simple date and so forth. And it was announced in February. So this was a big deal. This was something that some of us have been looking to for many years. For me, more than 40 years. I was offered a job on LIGO 40 years ago, and I turned it down to do other things. And because I thought it was too far away, but it was way further away than I thought it was. And okay, so here's what's going on to explain what that waveform is. So you have two massive objects, either a black hole, or in this case, it's white for neutron star, but it doesn't matter. You have two very massive things that are orbiting around each other. Because they're emitting gravity waves, their orbit will get closer together because they're losing energy. And that's called the end spiral until they eventually get together and they touch and they merge. And then they ring down because now the black hole has an odd shape and it's got to become more spherical or matching to what's going on. So the waveform shows the orbit going on. It shows the orbit getting faster because it's getting closer, and the amplitude of the gravity wave strain getting bigger until it merges, and then there's a ring down. So that's what you were seeing and what they claimed was a great event. Okay, so let's go through this event more carefully. So this happened to be at the time of the Brexit vote, so I thought it was nice to put a picture of the black holes orbiting around, Great Britain. Unfortunately, if we could turn down those two spots, it would help some on the density. So this is the scale size of what was going on. At the end, the black hole at the end ends up to be about the size of London. That's the scale size that you were talking about. Okay, so the source distance is a 1.3 billion light years. The heavier one was 36 solar masses plus or minus 5. The lighter one was 29 plus or minus 5. The merged event was 62 solar masses, and the energy that went out in gravity waves was 3 solar masses. Now, that doesn't seem like a lot, but it's a lot. That's 50 times brighter than the sum of all the radiation from all the stars in the visible universe. This is the most powerful event ever seen, and because it happens, all that 3 solar masses come out in less than half a second. Most of it within less than a quarter of a second. Right? So it's very fast. So power is energy over time. The shorter the time, the more powerful. The things that used to be the most powerful were gamma ray bursts. This is a factor of 3 to 10 more powerful than a gamma ray burst. So this is a big deal. One more thing, you can see the size of the orbit on the top, and in green is the speed. You will notice that just before merger, it's going more than half the speed of light. The orbital period, the orbit are going around at more than half the speed of light. That tells you how hard it is to make gravity waves. You need 30 solar mass objects separated by a distance which is basically the Schwarzschild limit, going around at nearly the speed of light. And then you get big signal. Only it's not that big when you get a billion light years away. Okay. So this is a sonogram. There's the time in seconds and the frequency of the waveform you're seeing. And this shape that you see, you actually heard 2 different sounds. The shape you see is what people who study bird calls, or sometimes bat calls, do. That is, they plot versus time the frequency of what's going on. This looks like a chirping sparrow. This is called a chirp because it's rising in frequency. Many birds have a decreasing in frequency, and bats have decreasing in frequency. I leave it as a quiz to the physics students. Why would you chirp high frequency first and low frequency lower if you're trying to see with sound? Right? That's an interesting problem for you to do. So here's what the events look like, and you compare the data from Hanford and from LIGO. Okay? And so this is something that we've been doing in some parts of science for a long time. It is sonifying what we hear and see in the data because our brains can process. It used to be our hearing was the best way to do a Fourier transform, but now computers have overwhelmed that. But, okay, now here are the black holes if they're in a galaxy and you had high resolution and a star, so they're really black except for the light shining on there. And you can see the stars behind it, their positions move because space-time is being moved, and the waves are going out. And when they get together and touch, they suddenly settle down, but the wiggles in space-time take a little longer to settle down. So That's what we could have seen if we only had great telescopes looking at the right place at the right time, but we'll see. Still like to have those lights down. Okay, so let me talk about the earlier attempts. We cover this in our article in a little more detail, but I have some more pretty pictures. So we'll see. Let's talk about what the earliest attempts were for looking for gravity waves, okay? And in a slightly different order, this is the first time we knew that gravity waves was real. This came at a critical time. The next thing I'll tell you about is the person who pioneered looking for gravity waves, thought he detected them, excited the field. Everybody then was very disappointed because they didn't detect anything. But then Hulson-Taylor discovered a binary neutron star that was very well behaved, which was Gratius. And it is two neutron stars orbiting in very tight orbit. The orbital period is just under 8 hours. And you can see, compared to the size of the sun, what their orbit size is. And then you can say, okay, suppose general relativity is the only thing that applies here. There's no dust or plasmas or anything in the way. What should the orbital period change by as a function of time? And you have this sort of quadratic curve. So you see the line there, it's a prediction of general relativity, and the black spots are the data points where they measure the orbital period, and it's changing by 76.5 milliseconds per year in terms of the rate of change. And if you're really skilled, you'll notice one other thing. If you're a great observer, there's no data point where that arrow is saying gravity prediction. You'll notice when they got the Nobel Prize, 1993, look where the data is missing. The Nobel Prize kind of disturbs your life, makes it hard to keep your, they were having to make observations all the time to measure the period of the orbit very precisely, because you have to keep track of every 8 hours it's going around, and you have to measure and count that very precisely. Okay. Fortunately, they did go back and began measuring again, and you can see the data points extending out. I only showed it as far as 2010, but it's falling right on that quadratic curve of, spiraling in. So from this, we know that general relativity's prediction of the gravity rate seems to be very accurate, and there therefore is indirect evidence there are gravity waves, so that was very important. And the other thing that we know is there are definitely neutron star pairs that are orbiting together, and LIGO was designed specifically to be able to detect neutron star binaries merging. It is optimized for that particular part of science, because that's what we knew at the time when that was going on, and I was following this. I actually taught a course on relativity physics, and it was one of the problems and examples I gave. And we didn't know how many black holes there would be, especially in binary pairs. So it turns out the rate that LIGO is thinking they're finding it is roughly more than 100 times the most optimistic prediction people have. So I'll mention something about that later. Okay, so at least we know that, but let's go back a little bit in the history. Here's the guy that really started the field up in a serious way. He was a graduate of the Naval Academy. When he finished serving his term, he went to work as a electrical engineering physics professor at the University of Maryland. His name is Joe Weber. And turns out he was a very good experimentalist. He was looking for interesting things to do. And he ended up coming out with a detector called the Weber bar, because he was the first one to push it. It's a resonant frequency detector. We'll see that. And the problem is, not long after, some years after he started doing this, he started claiming detections. And he started a bunch of people in the field that then got very unimpressed and depressed about the field. And if it wasn't for Hulson-Taylor, and then the idea of the laser interferometers again coming into the fore, that the field would have been dying out. Okay, so here's a picture of Joe Weber in the lab with his Weber bar. It is simply a huge piece of aluminum made as the best crystal as possible, and that means it's a very high resonance, very high Q. In the center, there are detectors to measure the wave. You're looking for a standing wave, so you don't put them on the end because the end is fixed. It's in the middle where the amplitude should be going up and down. That's why the detectors are there. So the frequency, it's a resonant frequency. Somehow the sound didn't come on. I'm sorry about that, but I have the note, and this is a picture from a Chinese historical soap opera, and it says, "The concubine doesn't sing." I believe that's what it says. Okay, and what was going on? Oh, that's the tone, finally. That's the tone you were looking for. You were looking for some gravity wave to come through that has significant power at that frequency, and then that would excite the bar. Okay, now you are familiar with something like that. If you have a crystal wine glass, it has a resonant frequency. If you set it on a table or hold it out carefully, if you sing the right note, it will resonate, and it will eventually build up energy and break. Same idea as this thing. And so the opera singer, though, can swing up in the notes, and when she or he finds the resonant frequency, it's usually a soprano because the resonant frequency is high, you can just keep that note and cause the glass to build up energy and break. And so the whole idea behind this detector is to hope that there's a continuous set of gravity waves coming out that have a strong component at 1660, and will excite and build up the energy in this detector. And it turns out, though he claimed there wasn't, the total amount of energy needed to excite that was quite substantial. You needed roughly the 2 to 3 solar masses coming from the center of the galaxy, in order to be able to power this. And that's a lot. The galaxy began to come apart. And so people, both experimentally and theoretically, sort of, said you didn't get it right, and it made things upset. But actually, he's been resurrected a little bit, because now one of the prizes of the American Astronomical Society is for the great observer, great instrumentalist, and it's the Weber Prize, and so forth. But the other thing you have to realize at the time, a very early time, he gave one of the first public lectures on laser physics, and he and one of his postdocs actually thought about making a laser interferometer to detect gravity waves, but concluded that lasers were not anywhere ready for that, and they were correct. Lasers were far from being in position to do that. However, now that's the first 20 years of looking, 40 years of theory, 20 years of looking, now 40 years of LIGO to get the whole 100 years. Eh? So in LIGO, the originator of the LIGO design was Ray Weiss, professor at MIT. He had to put in a progress report every 6 months or quarterly to an Air Force grant he had that funded this research, and he put in one of the reports, the design for a laser interferometer. It turns out he didn't know, but in roughly 10 years before that, 2 Russians had proposed using a laser interferometer for this, but they didn't have that. And Vladimir Brzezinski, who was a really outstanding experimentalist and very smart in theory too, in the Soviet Union, tried to resurrect it, but things weren't ready yet. So, and that's Ray in his lab. So I met Ray when I was a student and interacted with him for a long time. He was chairman of the science working group for the Kobe satellite. Okay, so here's his quarterly progress report, and that's the sketch for what LIGO was, what was going to eventually become LIGO. Things are different now. You have to put out a lot more detailed papers and so forth. And this was a result of Ray being asked to take over the course that Steve Weinberg had been teaching. Steve Weinberg was teaching a course on gravitation and cosmology, which eventually became his textbook. And then he was lured away to Harvard with his wife in a dual positions. And the department needed someone else to teach the course. They asked Ray to do it. He taught it. And when they got to the part about gravity waves and Joe Weber stuff, he couldn't understand any of it. So he ran this outside seminar with his students, and they came up with this idea of the interferometer, and he started working through it. Okay, so LIGO was co-founded in 1984, and then began as officially as LIGO in 1992. And there were 3 critical people. Originally, it was Kip Thorne and Ray Weiss. Kip Thorne, you should know, as a theorist. He wrote a book with Wheeler on gravitation, which is humongous. We keep saying someday it's going to just go into a black hole. And much more recently, with Roger Blanford, he wrote textbook on undergraduate physics that's also kind of thick and everything. And so they said, all right, we need some experimentalists at Caltech to make this thing go on. They tried to get Brzezinski, the Soviet Union wouldn't let him leave, and then, you know, they were looking around for who they might get, and Ray had heard of Ron Drever, who was very famous with Drever-Hughes experiments and some other things he was doing, and he just started doing some stuff on gravity waves, and they convinced him to spend half time in Glasgow and half time and whatever. Now that turned out to be good and bad. Drever was very fast and very good. He got ahead of Ray Weiss, who was working slowly with just a couple of students. And but Ray Weiss and Ron Drever could not agree on anything, and there were fights all the time. It probably delayed LIGO on the order of 2 or 3 years, the fighting. And at the time, Kip Thorne couldn't mediate because of his experimentalist. So eventually, that's how Barry Barish got called in to do this. And the issue would have been there would have been 4 people you want to put for a Nobel Prize, but during the time we were doing the reviews, Ron Drever died, and so that made it possible for the other 3 to get the prize easily. Okay, so here's how the thing went, right? So in late '79, MIT, which was falling behind Caltech, said we got to think big, of course, going to the next stage. So they gave both Caltech and MIT money, but less to MIT, and MIT kept falling behind. So by '83, Ray was worried about losing this was going on, so he went and convinced the NSF to give him funding to do a study with a company to try and see what it would take to make one that could actually measure things from astronomical distances. And so I was around at the time, and there was a brand new person who was now in charge of gravitation, a subfield that didn't exist in the National Science Foundation before that. Anyway, the first discussion of it was going to be 30 million. When the proposal came in, it was 100 million. When it actually got built, it was 325 million. And when it got upgraded to LIGO 2, it got over 600 million. So it got expensive over time. But they did then give partial funding to MIT and Caltech to be doing the development and to prepare for the construction. And with all the problems that were going on and trials with other people, eventually they pulled Barry Barish in. He truly understood how to run a big project and what was going to be needed to get it done, and separated the scientists from the engineers and the scientists that were working on the actual hardware, and kept the fights isolated on one side. So LIGO did not start until 2002, and it ran to 2010. They would run for a while, stop and fix some of the problems that existed, run again, and so forth. And then finally in 2010, shut down for 5 years for the big upgrade to Advanced LIGO. Now, Advanced LIGO was doing the same thing. That first event was seen during the engineering checkout. They declared that just before that, the actual data-taking run started, so they backdated the deed a little bit. And but there was a run. Then it was shut down, and some things were tuned up. And then there was another run in which Virgo was operating for that run. It's shut down now. They're scheduled to start up by March of the coming year, although I know one of them is running behind schedule. So the total cost up until now is about 620 million for the US, and on the scale of 400 million euros in Europe. Okay, so the Hanford one is in the desert up in Hanford, well, it's dry, arid area, and the Livingston one is in the swampland of Louisiana, and you see the 3,000 kilometers distance, and you see how the thing goes in terms of what happens, but it's just 2 identical L-shaped pieces. There's a central house, there's 2 long arms, 4 kilometers long, with mirrors at the end, and I'll explain to it a little bit more how it works.
A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The 2 beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
and you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
It sounds pretty simple, huh? Well, the scientific concept is pretty simple. It's the engineering and execution that are really difficult. It's an unbelievably complex instrument when you actually get down to the engineering. The present Virgo that's getting ready to come on sometime this spring now has 2,000 sensors and processors monitoring all the things that go on. And I'll show you a little bit of why that is. But also they exaggerated the wavelengths. You only move a tiny fraction of a wavelength. And so you have to be more precise. You have to have more powerful lasers, many things.
In an interferometer, a laser beam is split into two beams. Mirrors reflect the beams, so they meet again at a starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector. Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors, before returning to the beam splitter. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at most about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world. While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the super attenuators. Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. We can pick up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
To measure the gravity waves than it looks like, but still, I mean, 40 years is a long time, but it did take that long, and they've been working hard on it with actual hardware, of learning how to make the hardware better, learning how to vibration isolation, learning how to do all these things. And we're now approaching the quantum limit, and some of the new runs will include quantum squeezing of the laser in order to broaden the kind of things. So there's a tremendous effort involved here. Whoops. Hopefully. Oh, well. Oh, sorry. Now we got back. Okay, so I'm going back to the, if I get response, back to the announcement and to talk a little bit about it. Here's another simulation where you can actually see the black holes as black. Underneath you see the distortion of space-time, and there are even going to be little arrows to point out which way trace particles would go. And you can see the last half second of the life of these black holes as individual black holes. And they're radiating away gravity waves, which are distortions in the fabric of space, and that are propagating outwards. And as they get closer, they will eventually distort each other, and you'll actually see, if you look very carefully at the frozen moment, there are two horizons. There's the apparent horizon and the event horizon. So we slowed it way down here for the last 6 milliseconds. There, you can see two horizons exist, and then it merges and rings down. And the ring down is pretty much complete by 200ths of a second. And this, disturbance in the space-time, the ripples in space, propagate out at the speed of light. Okay, and so here's the data that I showed you before. And you do numerical simulations to see, you try different masses, try different orbital inclination, everything. You find the one that fits the data best, and you fit them together. And it's actually moderately complicated in terms of what's going on, but there have been additional measurements found. But if you have two things, and you measure the time to each, there's a circle in the sky which will give you that same time delay, and you're sensitive in one direction. So there's one sort of arc on the sky, which is the most likely place from which the gravity waves originated. But that's a huge fraction of the sky, and that's a problem. That means you didn't know really where to look in order to see these. And so what people do was that there were the two detectors in the United States, two detectors in Europe. Virgo was behind schedule. Again, it's still in the same thing. And GEO 600 wasn't big enough to make these measurements. Since the early discoveries by LIGO, they've signed an agreement in India to build another one there, and the Japanese are building sort of very high-tech underground gravity wave detector, but it'll probably be available sometime after 2020. They're a little bit behind schedule also. So why do you want more detectors? Well, you want them to be online more, but you want to have more baselines so that you can have intersecting circles and you can see things better. Okay, so here's the LIGO's growing universe. I'll zoom it in a little bit. So red was the original LIGO. Yellow was when LIGO turned on. And eventually, when it reaches full sensitivity, it will go out to this blue circle. And you can see called out a number of superclusters. A supercluster is a group of a very large number of galaxies. So you'll see the Leo, Pisces, Perseus, and Perseus, Pisces, and Shapley supercluster. Those are ones where you see more and more galaxies. So every time you gain a factor of 2 in sensitivity, which is their goal between major shutdowns, you gain a factor of 8 in volume. You should gain a factor of 8 in rate. So we're hoping that when LIGO turns on, it will, and Virgo turn on, they will be seeing events at 8 times the rate they were seeing it previously. They have 6 good events so far. and the binary neutron stars. So we can anticipate what's going to come forward, and this is going to be a growing field over the next 20 years, but the next few years is going to be extremely exciting as they reach bigger and bigger volumes of the universe. Okay? So as I was asked to give a talk to the Nobel meeting, and as I was preparing the talk, this cartoon came out. These guys, how do you know these guys are astronomers? They're wearing white coats and they have a telescope over there, even though the gravity detector is all done by computer and by whatever, but they're listening, but outside is the guy. But it turns out the next day, there was another event.
1.4 billion years ago, two black holes performed a cosmic dance. They spun around one another, coming closer and closer together until finally they collided. This dance created ripples in the fabric of space and time, also known as gravitational waves. In December of 2015, those gravitational waves reached Earth and were detected by an instrument known as the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. Scientists with LIGO announced the detection of the two black holes on June 15th.
This one has a higher pitch, if you remember.
This is only the second time that scientists have ever directly detected gravitational waves. The first detection, also made by LIGO, was announced earlier this year. Currently, all other telescopes and space observatories study the cosmos by collecting light or other particles. But the black holes detected by LIGO are not expected to radiate light. So by looking for gravitational waves, LIGO is illuminating otherwise invisible sectors of the universe.
So this last part was an ad for the NSF having spent $500 million on the detectors, but it's also true. Okay, so, you know, you can look at the data, and this was very different. Notice how much longer the waveform is. It goes almost a whole second. You see many oscillations, and that's because these were lower mass. They're in the frequency range which LIGO, more in the frequency range which LIGO was designed to detect. Therefore, it saw it more often and got to reconstruct it very much. And you can even see the very raw data, which they don't usually show because it's mostly noise, but it even got a peak that stuck up out of the noise. Okay? So at the time of the first run, there was the September 2014 event. That's the biggest, most powerful event seen, but only lasted a very short time. There was a potential detection, came in between, but it wasn't quite strong enough signal noise to do. And then there was the second fully claimed detection, which happened just after Christmas of 2015. And they ran a little while longer, and then they shut down for upgrade until they have the second run. And the second run had a similar kind of experience, but we'll see. So so how do we know, let me skip over these. How do we know what we're doing, right? So you see the best fit for the frequency of the period for the December 26, 2015. I think LIGO made a mistake, so I put a 5 above it. And their best fit for the September one, and so forth. And you see how they look, and you see what a binary neutron star should look like theoretically. Much higher frequency, or significantly higher frequency. It's because these are lower and lower amplitude. These are lower masses. These are 1.4 solar masses typically. And they can get much closer together, therefore they can orbit much faster before they merge. And the best fit is very different. It's much more massive objects. Just the frequency here tells you an effective mass of the operating system. It's called the chirp frequency. And it tells you, it's a formula that's related with the two masses. And it just tells you the mass that's going. So we know it's not neutron stars. We know these must be black holes. Or at least they're heavier and they fit in a space which is comparable to neutron stars. Okay, so here are the observations. September, the startup run was moved a little before it was supposed to actually be. And then this potential event, and then a gap, and then the Christmas event, and then the shutdown. That was the first run of advanced LIGO. So it's pretty good. You've been working for 10 years with the big hardware, big money, see nothing, and you turn the new one on, and you got a fabulous event right at the beginning. Okay, and here are what the events look like. The one on the top is the not confirmed event, but likely an event. And then you see the two gravity waves. You see them as part of a big arc around the sky where you would observe them. And that's just because you have two detectors and you're just doing timing. If you should have had Virgo, if Virgo had been running, that event would have been localized by the crossing circles to a very relatively small area like that. And so there was very much pressure on LIGO to get running for the next run. And even though they weren't completely ready, they did get running. And right away, there was another deja vu. They found another event fairly soon after the run started. They tried to upgrade both Hanford and Livingston. The upgrade to Livingston had worked. They had to go back to part of the stuff had to go back to the old configuration for Hanford. So you can see Livingston had roughly twice the sensitivity, that is twice the signal to noise, as Hanford. The strain was the same at both. This is just the signal noise plot. And then you see Virgo barely has a signal, but it's there. You can see the chirp, the sonograms, and you can see the signals in comparison. And Virgo has a lot of noise, but when you beat it against the template from the other two, you can actually see it's a positive detection. And that's important because that allowed proofs that Virgo was starting to work, and it also allowed the localization of this event to a better way. So here's the picture of the actual Virgo observatory. It's in farmland just outside of Pisa, Italy, and this was during a time the crops are growing, so it's green. Okay. So Virgo provided improved location. So you see the yellow banana, which is from LIGO, and then the first result out of Virgo is the green banana. That went out in a telegram right away at localized spot. And then they did the more careful numerical runs, more detailed numerical runs, and got this sort of purple spot as the localization where they think it can go. There's a lot of calculations that have to be done to try and find the best fit. Okay, so what that did was allow the localization down to this area with a little tail off that area. So that was showing that the promise of adding another detector is actually allowing you to limit more what's on the sky. It's still not small enough for regular astronomy, but it's getting in the range where you could try and do searches. That becomes relevant just a few days later, 2 weeks later. There's another, well, sorry, this is one of the Day of the Dead pictures. I forgot to upgrade this. I have one which has all the runs. And so the very first event is the big event on the top where it makes the 62 solar mass one. Before that, down in this area, these are the known black hole masses from X-ray binaries, right? Where one of the guys is a black hole, and it creates an accretion disk, and you get to see the X-rays from it. You can measure the orbital parameters, you can measure the masses. And so this was what was known at that time. We actually searched through the literature and found some more later, and so did other teams. But you can see these guys are much more massive. Even this not proven event is fairly more massive. This guy, who was the third event, is sort of in the range that it could be in the conventional stellar motor. This one is heavier, and this one is heavier. These are the various ones that were found at that time. And now I have one that's the Day of the Dead one, which shows a few more stuff. These are dead stars, right, in what our way of thinking. I've been worried about where these heavier solar mass stars for quite some time. I tried looking at various ways you can get them and seeing if you can make them primordially and have them be the dark matter. And in the end, I concluded and wrote a paper with two colleagues. One is Jose Maria Diega, and the other is Tom Broadhurst. Unfortunately, he's Spanish, not Mexican, but it's the thing, in which we claim that these events are not really at these masses. They appear to be at these masses because they're viewed through highly magnified gravitational lenses, and that makes them look closer and bigger, and therefore stronger. And that everybody says, well, that doesn't make any sense, and they argue with us a lot. We've been having trouble. But because everybody, you can do the simple calculations to get that kind of magnification is less, it's about a chance in 10,000. So if you've got 6 events, you know, should 3 of them be lens? And the answer is no, unless you say, I had 1 million events and I picked the 6th brightest one. Then half of them can be lens. Right? And so at least I'm eagerly waiting for LIGO to turn back on, because even after 3 or 4 talks to the LIGO people, only a small fraction of the LIGO people you know, are saying this may be right, because there's a lot of them that want to be able to just make Hubble diagrams and things without having to worry about lensing and so forth. But we'll see. So what I'm saying is there are a lot of new science and unsolved science coming along, and some of them we may solve in the next year or 2. Some may take longer. Okay? So this is just for the engineering people who are here. Here are the noise versus frequency, the stream noise, from the detector itself. If there's no gravity waves, you still can take the raw data and run a Fourier transform, and you can see what's going on. This is what Virgo is doing. Right? This is what LIGO is doing. The Virgo has a cutoff more quickly because it's shorter and because it's lower power. This overall shape is set by the uncertainty principle. You've got 40 kilogram mass mirror, and you got the delta X, delta P from the laser, and you have to figure out the position between the mirrors. It's really a kind of thing like that. That's why squeezing is starting to become back, to try and flatten out this, because these were designed to be looking in the frequency range for a neutron star, neutron star. This is Hanford and LIGO previously. This is the goal to come to now. And here you're leaving one resonance in, because that's the resonance, primary resonance of the mirror. The mirror has thermal noise in it. It would cause vibration. If you can have a very strong resonance you keep, you can put most of the thermal vibration noise in that and cut that out of the data when you analyze it. The long-term goal for advanced LIGO, before they have to ask for more money, is this green line. So it's flatter and so forth. And there's a problem here because the lower branch of the uncertainty principle and the ground noise give you a really hard limit there. So those are problems that are still having to be solved to figure out how to make this stuff work even better in the future. Okay, well, sorry, I'll skip over these. But this is not the only way we're looking for gravity waves these days. The first guys to discover gravity waves directly are the ground-based interferometers. There are coming space-based interferometers. The one that's best known is LISA, Laser Interferometer Space Array. But there are also 2 Chinese institutions, one from the province of Guangzhou, and the other from the Chinese Academy of Sciences to put laser interferometers in space. Laser interferometers in space have a big advantage because they orbit around at the Earth radius from the sun, and therefore you get many different, it's like having a lot of different ones, provided you watch for a whole year, you're looking in many places. So it's like having one here for a while, and then one over here for a while, and one over here for a while, over a baseline that's astronomical unit sizes. But the other thing that already exists are pulsars that are out in space, the same neutron stars that we saw in the binary pulsar. If you look at it, one in every couple of 100 to a few hundred pulsars is an extremely stable clock. You know, some have noise because they have star quakes and other things going on, or they're accreting material, but some are extraordinarily stable. So you can have the neutron star out here spinning around, sending out a signal, and a gravity wave comes through, and it'll move it slightly closer and slightly further away, because now you're talking huge distances, and so even 10 to the minus 21 causes a big difference. And you can set limits on the gravity waves due to just timing the arrival of the pulses. And if you have a nice array, if you had a pyramid array in all different directions, you could actually tell the direction and the location of the gravity wave. But the one that I've been paying attention to and wrote paper about, the first paper about 25 or 30 years ago, and then has been followed up, is you should see a certain polarization pattern in the relic radiation from the beginning of the universe if there are gravity waves produced in the extraordinarily early universe, in the teeniest fraction of a second, 10 to the minus 30 seconds, that kind of level. You should, 10 to the minus 34 seconds, you should be able to see these polarization patterns. And this is actual data here from an experiment called BICEP2, which claimed to discover this, but it also turns out, though they picked a low dust part of the sky based on our maps from our Planck satellite, it was also a place where the magnetic field of the galaxy is very organized. And we did a joint paper with them, and that could be also explained just by the dust in the magnetic fields in our galaxy. So there's still ongoing experiments to do that, and there are proposals for even more experiments. There's going to be a whole series of experiments looking for this kind of phenomena. And you want to do that because it tells you, each one of these, this tells you about black holes and neutron stars. This tells you about, if there are some 30 solar mass ones, you can see them in LISA. But it tells you when two galaxies merge, they have very large black holes in them, and the black holes eventually come together and will orbit in. And you can see them from anywhere in the visible universe. It doesn't matter how far away they are, as long as light can get to you, you can detect them. Their signal is so strong. One of the issues is they're going to have confusion noise between all the black holes in the galaxy, making it's like an orchestra. You've got to be able to hear the different instruments carefully. And the pulsar timing arrays should get to be better as we have better radio telescopes and so forth. And the microwave background, a lot of things are going on to try and make these measurements. And it depends on nature. It depends on what is really the energy scale of inflation when space and time are made. Is it extraordinarily high, or is it a much lower one that is below the backgrounds from our own galaxy and other sources? Okay, so this just tells you from the Big Bang, there's a whole series of things. There's the stuff from the creation of space-time, but there are also stuff from symmetry breaking and other things extend over light. For the supermassive black holes and binary mergers, when galaxies merger, they show from both the radio pulsar and so forth. And if there are topology effects like cosmic strings, they will show up here. This actually provides the best limits on that. And here, you've got other things that are going on, but eventually, there's a whole source of astronomy you could do with gravity waves, provided you put the detectors in place and nature is kind to you, that there aren't terrible problems to observe it. And this was just an example. If that 30 solar mass black hole had been detected by, at that time it was called ELISA, detected, it could be tracing it for on the order of up to 10 years, measure its position to much better than the degree, and estimate its time to within a few seconds of when they would merge. And then the LIGO and optical telescopes could be watching that spot very carefully to see what happens. So that was something that was really recognized only shortly after the announcement, right? You see that paper was written shortly after the actual announcement. And so there's various things. I should skip over this. We've had a lot of astronomical implications about the mass of black holes. My argument is there's a bunch that are on the right that aren't really at that mass. They're lensed, and they're actually lower mass and further away, and so forth. We have tested general relativity, right? This is Einstein's legacy. We use general relativity in astrophysics and cosmology because gravity is one of the most important forces, or the most important force on that scale. Everywhere else, we don't care about it so much. But here's an example of the various tests of the how well general relativity does compared to just doing an expansion of general relativity to allow extra terms and other things going on. And you see everything is consistent with zero added expansion. General relativity is holding up extremely well. It's been the champion for 100 years, right? And it's looked like it's going to stay champion for quite some time beyond that. And that is surprising because a lot of people don't like dark energy. Some don't like dark matter, and they want to modify gravity instead of do that. But you can't do it very easily. Solar system tests and these tests are allowing you to limit things extremely much. So why was this important? I'll get on this and I'll get to the neutron star. Well, this is the first direct detection of gravitational waves. 100 years after their prediction, Einstein is shown to be right again. They have the right speed, they have the right properties, and everything fits together. This is also the first observation of a black hole binary, right? And the formation of a heavier black hole directly. We've never seen a black hole form directly. This is the first time we've actually seen it happen. It happens. Usually it happens inside of supermassive stars exploding or in situations we don't know. And so my question mark, are there really a lot of things, real black holes being produced? It's hard to do it for various reasons. Are there really a lot of black holes with mass greater than 15 times the sun? or is our speculation that it's gravitational lensing going to be? This is the most luminous, that is the most powerful astronomical event ever detected, and this is a new, window on the universe. So that's a pretty good start. They get the Nobel Prize, right, for that. Well, for at least starting it and making sure it happens. Okay, but more happens. The colliding black holes mark the new era of astronomy, but we have neutron stars, which is the original goal of LIGO.
LIGO's hits just keep on coming. After its first detection of merging black holes, swiftly followed by finding 3 more, and then a Nobel Prize, the pair of gravitational wave detectors has made yet another huge discovery.
Actually Virgo.
On August 17, 2017, the observatory detected gravitational waves from 2 neutron stars spiraling together and merging. Just 2 seconds later, a so-called gamma-ray burst was detected by NASA's orbiting Fermi Gamma-Ray Space Telescope and its Swift Space Telescope. 12 hours after the wave was detected, a team from Las Campanas Observatory in Chile reported a new glowing optical source in galaxy NGC 4993 that was consistent with these findings. And with the advanced tip from LIGO, both radio and X-ray emissions were found a few days later, coming from the same neighborhood. Not only is this the first time LIGO has detected gravitational waves from a neutron star collision, it's also the first time that electromagnetic observations from conventional telescopes accompany the gravitational waves. At wavelengths ranging from ultra-short gamma rays to very long radio waves, the event was seen by observatories around the world. Because we now have visual information to go along with the gravitational waves, new discoveries are being made about the nature of neutron stars. The light coming from the collision showed spectral traces of lanthanides, a group of heavier elements towards the bottom of the periodic table. This strongly suggests that merging neutron stars have been responsible for the creation of heavy elements such as gold and platinum, a long-held theory. Not only that, but the shape of the gamma-ray burst was unusually weak. Gamma-ray bursts are usually so strong that researchers assume that the gamma rays emerge from 2 back-to-back jets that shoot out of an explosion like narrow spotlights. The weaker gamma-ray burst suggests it was produced when broader jets slammed into a cocoon of matter surrounding the merged neutron stars. While this finding is home to a lot of firsts, it won't be the last. Researchers are positive that with the large amount of gamma-ray events out there and the increase in both gravitational and electromagnetic detector sensitivity, we'll be seeing a lot more of these combination events in the future.
There's a little bit of that is controversial about the gamma-ray burst and so forth, but it seems now the light elements are made in the Big Bang. The intermediate elements, carbon-nitrogen oxide up past iron, are made in supernova. And a big fraction of the heavy elements are made in the binary neutron star mergers. And we figure we can ask for government funding because we can tell them where they can find 3 Earth masses worth of gold, just a little far away, right? So the other advantage, the other advantage is we now have...
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of 2 neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our Sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. researchers quickly realized these two fundamentally different types of waves could have come from a single neutron star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma-ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with the target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
Okay, well, I'll skip through some of this, and I wanted to get to at least the neutron star. Two black holes, when they merge, aren't expected to produce any light unless things are extremely unusual. But two neutron stars, some material, a significant fraction, but still a small fraction of the neutron stars, eject their material out and form various things, and eventually collapse together to form a black hole with the relative jets coming out. So that you have, in this example, of something that's on the scale, I can't remember the exact distance, third of a million light years away. That's right. Third of a million. Anyway, all right, I'll get it right. I think it's kiloparsec. I have to work through that, but I think it's third of a million light years away. The gravity waves and the light arrived within 2 seconds of each other, and you expect the light to take longer to get there because it takes longer to form the jets, right? So I was expecting around a little over 1 second. It's 2 seconds. That might tell us something about how long the neutron star lasts, the superneutron star lasts, before it forms the black hole and the jets. But there's lots of problems to be solved yet. So this is something about crashing new stars being able to make gamma ray bursts. This is the wrong one. Let me skip that and go to this one. This is just to show you science can be pretty. It can be aesthetic and artistic, although NASA overdid it a little bit. This is the high-speed relativistic calculation of the ejection of material and the merging of the neutron stars. And I showed it to you just to show you how complicated it is, but also to show you it's actually quite beautiful. So you get a disk, you get a cloud, and you get a jets. This doesn't get to the jets here. Okay, you were supposed to think it was pretty. And it's pretty amazing when you think about what's going on, because in fact, you have two sort of 1.5 solar mass objects coming together, throwing out up to 1/3 of a solar mass material around, which is essentially all neutrons, and they go through what we call the rapid neutron process, and they eventually turn into the heavy elements out in the cloud and the disk. And the jet has completely different sort of origin and what goes on. But this may be where some of the metal in here came from, and the heavy metals anyway, at least the stuff in your phone. And that's quite surprising that we have all these different sources for the material out of which our world is made. So I want to come to the end now because I'm sure I've run late, and I wanted people to be able to ask questions and to think that maybe they want to read this book anyway. So thank you. So I did have the slides for the stellar graveyard. This is everything we collected to date.
Hi. Thanks for your lecture. You mentioned that there was no. Right? You mentioned that there was no evidence for deviation at some moment, but I don't know if this question makes any sense. But has the topology of the space-time any impact on the strength of gravitational waves? And my second question is, how does one get a grant for $600 million from NSF?
Okay.
Which one do you want to answer, the first or the second?
Okay. So the quality of space-time? What was
it's the topology.
The topology
first.
Yes.
And the other one is
okay. So on the scale, so the topology is a problem I had a graduate student work on, and she did a really good job. And this is Angelica, the elevator cluster. And we did some work together, and she did part of her thesis on it. We also wrote a paper with Alexei Starobensky, who's a Russian, who's one of the architects of the surviving few inflation theories. And he won some prizes for that recently. We looked carefully at the question of not only the geometry of the universe, but the topology of the universe. And using the fact that the microwave background has some very long wavelength structure in it, you can show that the universe topology is simple out to a very large distance, a distance which is roughly 10 times the black hole distances and roughly 100 times the neutron star merging distance. So as far as these observations and calculations go, you can treat the topology of the universe as a simply connected universe. So we can just use general relativity and don't take into account that. Now, if you go completely to the scale of the universe, you do have to worry, is the universe somehow connected? Not simply, are there handles on it, are there other things on it? But for the scale, small scale, like 1 million light years, it's not a problem. And even 1 billion light years, it's still simply connected. It's only when you get to a really huge distance. Okay. So now, how do you get a grant for 620 million. Well, it was 2 grants for 300 million. Right? Okay. So the Kobe satellite cost 325 million. The Planck satellite, $1 million, US dollars. The Planck satellite, which we're just finishing up, was nominally 600 million euros, but if you add up the other expenses and the salaries, it's clearly approaching €1 billion. So you've got to have a really good idea and a good press, and you got to go forward. But let's talk about LIGO to begin with. You saw, I traced a little bit, I was asked by the brand new PhD, he was fairly a brand new PhD in general relativity and gravitation, and he joined the NSF as a program officer, and they gave him the portfolio for gravity, right? If you could imagine, right? I mean, gravity was just part of fundamental science before, and they created a new division, which he got to be head of, to do that. And I happened to know him and run into him. I was going to Washington, D.C. for other reasons, and I happened to, when he was moving there, and I happened to know him and talk to him, and he said, you know, what do you think about, you know, looking for gravity waves? And I said, well, I think that's a good idea. The NSF generally does small projects. He says, I think we should do a big project, and because then Ray Weiss had come at that time and talked to him. And at that time, they were quoting a number of 30 million. And I thought, well, 30 million is a big investment, but it's worth it. I encouraged him to go to his supervisors and say that's a good thing to do. When they finished and put the actual proposal in, it was 100 million. That was sticker shock. Yeah. It's like you go in and to buy a car and they're advertising it's very cheap, and they say, well, you really want this model, and it's only 3 times this much money. And that's sticker shock. The issue is then you have to go through both in Europe and the United States and somewhat now in China, which is putting very substantial amounts of money in these projects and the projects. You have to go through a process in which you do studies, you do prototypes and studies, and you show the basic concept of work. And so LIGO was not given that money just at the beginning and said, go. They were given money to build prototypes and to do studies and to do that. And then at various stages, they went back for reviews and updated proposals and updated following along what's going on. And they were given the money then to go to the next stage. So the funding profile was low, stepped up, and then went way up when they went into the construction phase, because then you hire a lot of engineers and you're buying a lot of parts and so forth. And so you go through, typically in NASA they have phase A, B, C, right? And C is construction, D is launch, and E is operation. So they have phases, and you have to go through gates for each one of those. You're not given all the money up front. You have to do that. And so you have to create a proposal that's extremely well thought out. You present that proposal, peer review and funding agency review approves that, then you go and do the next thing, and you put out a much more detailed proposal and so on. It's a whole series of things, and you earn that money. It's hard work to do that, but it still was very forward-thinking and risky for the National Science Foundation to fund this, because you didn't know for sure that would happen. The only thing you know for sure would happen was you would see neutron stars when you got to the full advanced LIGO. When LIGO was funded, they'd had to have been lucky to find anything, and people knew that. I mean, we knew that when we did the reviews, we did calculations. We knew that it'd have to be lucky that there was neutron stars merging in our neighborhood close to us for us to be able to see them, right? It's only when the full advanced LIGO is up are you guaranteed to be seeing them regularly. This one was kind of lucky, but not completely lucky.
Pregunta por acá.
Hi. I will try to explain you why my interest in this topic, and why I'm asking for you from the difference, obviously a part of your book, that if you could give me some information about the different books about this topic. I'm excellent of textile engineering, and I did my thesis about the spacesuits So I'm studying about the radiation, the UV radiation, and the different waves, especially this UV and X-ray, and how they can danger the spacesuits. So, but now my interest in, of the study is because the spacesuit, an astronaut used in a spacesuit just for some time in the space, but the other robots or some kind of naves in the space are pass more time in the in the expression of this type of radiation and this type of waves. So my interest in is because some kind of cloth could protect maybe these rods. So that's my interest in take more information.
Okay, so there are a lot of different answers to this. But no, I mean, there's different aspects to it. There's a lot of answers you give. So you don't hear very much about ultraviolet astronomy, although I have a colleague, a professor, retired now at the University of California, Berkeley, who actually got a satellite to do ultraviolet astronomy, and they found more things than people expected. The galaxy is full of gas and dust, and the mean free path for ultraviolet photons is extremely low. So people expected you couldn't see past about the nearest 50 stars, which is roughly 10 light years away from here. So there was the expectation that's a window. We have some windows we can see from the ground where the atmosphere is transparent. Ultraviolet is not one of those, right? And X-rays and gamma rays are not so much that. But there are some other places where you can't see. But once we get to space, we can now see most wavelength bands, but we cannot see very far in the ultraviolet because this material in the universe stops it. And we can't see at ultra low frequencies very far radio waves because they're also free electrons, and they disperse, their dispersion is such that they create a plasma frequency. If the waves are below that, their wavelengths are longer than that plasma wavelength, they don't propagate either. But there are windows all the way up except in the ultraviolet that you can pretty much see all the way to get to extremely high energy gamma rays. But the ultraviolet we're protected from twice, except now if we were in the ozone or the sun gets more active, then we'll notice it in sunburn. But the sun is really close, and so it doesn't get absorbed by anything but our own atmosphere. So this is an area which people have been studying, and that sort of been guiding people as to where you should go and do astronomy, you should go and look for things. But they also have to test that, because when you take and send satellites to space, they're exposed to things like ultraviolet radiation, which can ruin the early fabrics that were put around spacecraft were destroyed in a relatively short time. And people eventually went to gold. They would put this Kapton with thin gold coating on it to protect it, because you'd run into oxygen molecules in the atmosphere, or oxygen atoms, and they get activation energy, and they would essentially burn the outer material. And ultraviolet light would do that. And we also had to learn that there are electrons going along, and you have to make sure you don't get sparking. There's a huge amount of technology and knowledge to how to operate in space where you're not protected by the atmosphere and by the other things of the Earth. So there's a lot of things like that. Now, one thing I will say, because it's time to advertise it, Jorge and I, many years ago, did a conference together, and we realized at that point that going to all-inclusive resorts was great. So we started in Spanish, Cosmología en la Playa, in English to funding agencies, Essential Cosmology for the Next Generation. So we used to run every year a school which was roughly 50% Mexican, but we bring speakers in from everywhere to talk about what the latest topics and the most interesting things that are coming forward in cosmology, and try and expose the young scholars and young scientists to this kind of activity and so forth. And now we've gone to having it every other year, and I think next year is the year. And but I haven't been doing my share lately. I've been tasked with other things for a while. And but I am pleased to see it go forward. And there are now many opportunities for young Mexican scientists to get involved in astrophysics and cosmology, but in other parts of physics too. And so depends on your interest, and I'm telling this because it could be broader interest. Yeah. Depending on your interest, there is the possibility not only of getting to make acquaintance with people from other parts of the world, but also hear about the latest research and up to date. And we only make the students put out posters or give contributed talks, but we give them a prize if they do a great job.
Yes. Ok, gracias.
Okay, thank you.
Otra pregunta, si hablas en español la traducimos o quieres hablar en inglés y por favor breve.
Good morning, doctor. My question is, why is important to countries to invest in projects like LIGO? That's the question. Why is it
important to invest in projects such as
Okay.
LIGO?
All right.
Or any big
Okay,
project?
so there are several reasons, and the fact that there's curiosity and a cultural need to understand the world around us and understand the universe and know where we came from. There is a more important reason, and this is the one that funding agencies listen to, and that is the truly major revolutionary things that happen always come from what we would say in the United States for baseball, left field, things you never thought about. So I'll give you an example. Suppose there is a scientist, let's call him Röntgen, and he wants to know if energetic particles come from the sun. Would the Department of Health and Human Services give him funding to do this research? No, okay? He did this research, he's a careful researcher, and he discovered X-rays, and he wrote an article, and in that article is a picture of his wife's left hand, and you can see with X-rays, and you can see her wedding ring and her bones, and he published that, and then 1 month later, there's an X-ray machine in the Berlin hospital. Okay? So he pioneered from this discovery of figuring out if stuff came from the sun, the idea of looking inside of people in medicine without cutting them wide open and looking around. Now we have CAT scans and magnetic resonance imaging. We have many things. We do surgery now laparoscopically. Rather than cutting people open, we send little tiny probes up in and do heart surgery by looking inside of them rather than cutting them open. So that's an example of why you do research in areas where you don't think you'll have any relation to what you're doing. It revolutionized medicine. The only thing I saw in medicine before that would revolutionize medicine that kind of came from medicine was Pasteur discovering that life actually existed, and that diseases came from bacteria, right? And you could pasteurize things. That's why it's called bacteria. That's a guy who was thinking of medical problems and solving medical. Almost all the other major changes in medicine and health have come from completely other research that just happens to shed the light on that. You can think about that in other ways. So to discover the electron, who would pay someone to discover the electron 115 years ago? Nobody. What fraction of the world economy today is manipulating electrons? I can tell you because I've seen this, but if you look at the model they have of the economy, right, there's one box that says electricity and electronics. That's 62% of the economy of the United States at the time I looked at that. You understand how big an impact. So you fund stuff like LIGO because you learn how the whole fabric of physics and science fits together, but you may also come upon something that really helps you, but you also develop a huge amount of new technologies and ways of doing things. This is really a precision measurement. You're measuring 1,000th the size of a proton. A huge number of the advances in the world come from being able to measure things better, right? Positions, times, all this kind of, you don't realize how important measuring time precisely is to you unless you decide you don't want to use your cell phone, you don't want to look at TV, you don't want to, all those things depend on measuring time extremely more precisely than you would ever have thought that you would need to. So there is a strong reason for that. But the other thing that I was misquoted in the paper apparently, but 85% of the increase in the economy of the world comes from innovation, not from finding new oil, not from finding new minerals and so forth, not from a bigger population. Those are 15% of the increase of the economy of the world. 85% of the increase in the economy of the world each year is due to science turning into engineering technology, turning into new products, innovations, and new devices. So you need this continuous flow of science, basic science, to applied science, to engineering, to new products, in order to keep your economy doing. And it happens faster and faster. You know, when I was young, Korea was a very poor country, right? And they started concentrating to build up their science and so forth, because they realized that if there's a new discovery, even though they didn't necessarily make that discovery, they had to know how to interpret it. And so when LEDs and plasma generations, they decided they could make big screen TVs better than anybody. And so I bet your big screen TV is Korean, not because they invented them in Korea, although they invented some of the stuff in Korea, but because they had the scientists who understood the principles and realized this could become flat screen TVs instead of the same thing that we had for the 100 years before that.
Thank you. Thank you.
Thank you. You can tell.
Okay. Juan, esta es la última pregunta, y se nos está acabando el tiempo.
Hello.
Okay.
I have a very short question. It's a very easy one. So
sure.
There are a lot of students of science, and there are a lot of engineers in progress and all of that, and you look like someone who has been in this field of science a long time. So the question is, what is your inspiring word or your speech for someone who's starting in science, and what will be the tips or the advices for someone to succeed and go well in science in a world where it's sometimes harder, you know?
Okay, so I could say thank you for saying I'm old. However, the real point is, if you want to do science,
Smoot Cooper,
you have to ask yourself, do I really love to do this? Do I want to do this? Am I willing to work hard, learn the basic science and the mathematics so that I can contribute in a serious way to science, right? And there are many ways to do science. You can try and make these huge foray jumps. You can try and work with teams. In the future, interdisciplinary teams are going to become more and more important. So working with people, establishing trust and kindness is going to be extremely more important. But you still have to have the basic knowledge. So you may need somebody who has information technology knowledge, someone who knows physics knowledge, someone who knows biology knowledge to make some of these products. But the first thing is you have to have the burning desire that you love science and that you want to do something good with that science. You want to make something new and do that. And if you do, then you'll go through the trouble of studying hard and becoming an expert and being able to work with a team of people and make advances, right? Not everybody just puts on their white coat and stirs some chemicals together and I found the cure for the cold, because they haven't, right? But the most scientific discoveries come from recognizing things from here or from there and putting them together, or working with a team of people. You know, LIGO, the scientist concept was simple. The engineering concept is very complicated. It's a big team of scientists and engineers, but the engineers have the bigger role in the actual realization. Same is true of the satellites, the 3 satellites we're doing, hopefully the 4th satellite we're doing. Those were as many done by engineers, or more done by engineers than were done by the scientists, except for the hard part at the beginning and the end. We had to tell them how good it had to be. And then they had to make it, and we had to test to make sure it was good. And then we had to actually analyze the data. But the engineers had to make that possible. They had to make that realization. So you always now, if you do big science, have a team. There are still areas where there's small science, but often now it's going to be interdisciplinary. And you have to know your part very well to hold up the team.
Thank you very much.
Thank you.
Esas son todas las preguntas. Ya no tenemos tiempo, perdón. Viene el doctor Tufiño y cerramos el programa. Pues, les agradecemos a todos los que iban a preguntar.
Muchas gracias. Bien, tenemos, por falta de tiempo, pues ya tenemos que suspender las preguntas. Le agradecemos al profesor George Smoot su excelente, muy interesante conferencia y le vamos a entregar, en primer lugar, un reconocimiento por su participación y por esta brillante conferencia. Profesor Smoot, thank you very much.
Gracias.
Oh my God. Also, we're going to give, le vamos a entregar esta pequeña escultura, sculpture, de un artista mexicano, Claudio Bautista, que la nombró el inicio, the beginning. This is the beginning of the universe.
Okay.
This is for you, original.
Gracias.
How do you find the scientific community here in Mexico? Do you have any kind of opportunity to collaboration? In this moment, are you having any kind of collaboration, and particularly with the Polytechnic Institute? Well, on the
no.
Okay.
So here's an example right here, a living example. We have written several papers together, including the one that I quoted with Salvador about the history of gravitational waves. And he sent me last night a draft saying we want to talk about the draft today, but I told him I didn't have time to read it last night. We're working on another paper, but we have been collaborating on many projects over the time with many people in Mexico. I have some work I was doing with people from the University of Texas and another part of Yunnan. He's from Yunnan. What? Yeah, and he was doing computer simulations of the neutron star gamma reverse concept and black hole. Collapsing the supermassive stars, making black holes with jets punching through the stars, particularly that. So I have been collaborating with many people around the world, but it's been consistently over 20 years a collaboration with people in Mexico, and I expect to continue. This is the third time I've come to IPN, and the previous time was for the world premiere of the Mayan Skies, Cosmologia Maya, and that was a very big event. I gave a talk there, but the main celebration was that. We have actually a new planetarium show, which I've been trying to look for the planetarium director to find out if he's taken, called The Phantom of the Universe, which is about dark matter, and we want them to be showing that with Spanish words, a Spanish soundtrack rather than English soundtrack, but it's already playing in many countries, and I know it's played in Mexico, I just don't know if it's played. And so it's not that I haven't collaborated with IPN, it's mostly I've collaborated with other places, including Conacyt, and doing some reviews and support for Conacyt, but it's a whole collaboration. We found it together, I think Omar is here too, with Axel Dalmacara. We found that Instituto Avanzado Cosmologia, which has people from all over Mexico as members, and many of them come to the winter school, but we have other events and so on. So there has been a continuing collaboration with people in Mexico, and I hope it continues in the future. But I don't know about IPN yet.
Well, the second one, it's about, could you repeat some about the implications to study these massive events, and particularly the gravitational waves? I mean, in terms of the implications of the evolution of the universe, I don't know if the evolution of matter.
So the gravity waves we've seen so far are important because it's the first direct evidence for gravity waves, which was the last big prediction of general relativity, and it's now proven.
It allows us to test any modifications to the theory of gravity much more precisely. It let us see the first binary pair of black holes and the first time a black hole formed. We know black holes form, but we've never seen that happen. Now we've seen it happen. So there are many things that are important from the measurements today, but I tried to indicate in the talk that there is a whole range of wavelengths and frequencies over which you can measure gravity waves, and they can tell us about different aspects of the universe. What happened in the very early universe? The very early universe has many phases. There's the make of space-time, there's the changing out of the grand unified, there's all these symmetry breakings and things that happen in the first fractions of a second. And each one of those should leave gravity wave residues that should still be around in the universe. And do you think that making space-time is important? Well, yes. The gravity waves are part of that process. They don't drive it as much as they are inherent part of what's going on. But they can tell you about what was going on there, and we can see. And we don't know what else we'll find out, but we know in the center of galaxies are supermassive black holes, and galaxies merge, and those will orbit around each other, and they will produce big signals. So there are many places where we know there will be gravity waves produced, and we know we should be capable of detecting when our technology gets us there. And the technology we need now is to put at least 3 satellites in orbit with lasers going between them and have millions of kilometer baseline between them. And that will be happening in the within 20 years. And so there are many things, and it's going to let us understand the universe a lot more. How much it changes things is harder to say. And we know what a huge role that light, electromagnetic radiation, played in the history of the universe. We know the role dark matter and ordinary matter play. We don't know quite what the implications for gravity waves are. But it's very different. We think it's less, but it may be a good trace of what happened at the time.
Muchas gracias.
¿Ahí me puedes ayudar con las preguntas? Sí. Hola, Berenice Sánchez, reportera de la agencia informativa CONACYT.
So I have to say good things about CONACYT again. I already did an interview in Guadalajara where I said CONACYT was good. But the right-wing newspaper here says, don't depend on oil, depend on science and technology.
Bueno, pues estamos en medio en la transición de gobierno y el nuevo gobierno le quiere apostar más a la ciencia aplicada que a la básica. ¿Usted por qué diría que se tiene que apostar a la ciencia básica como el estudio de las ondas gravitacionales o los agujeros negros?
The new government now is going to, they want to support much more applied science than basic science. So what should be the reason why government should support basic science like research on gravitational waves?
Okay, so I think it's extremely important to fund basic science, and also science that takes that basic science and puts it towards application, but also then links to engineers and to new products. Science and activities are changing so rapidly that if you don't have people in your country who understand basic science, you will be behind in making new products. You have to know what's allowed and what's coming, what discoveries have been made and are starting to develop before you know what's important to take and put applied science to work on and to do that. Now, in the case of the gravity wave, my guess is it's many, many decades before that's applied to society. That's, high risk, a great adventure. Maybe something would be discovered, maybe not, but it's something that's important to humanity to know and understand. But there are many other examples. And so I gave the example of South Korea, where they realized it was important both to have applied science and fundamental science. And when the ideas of the LEDs and the plasma screens and I forget what the other one, LCDs, the twist LCDs, they realized that could be made into flat screen TVs. And they started they said we have to have a development project on that, right? But it it took the pure scientists to recognize that these discoveries were there and tell the applied scientists that you need to do that. And you have a TV, you own a TV. Is it a flat screen TV? Is it from Korea? Right? I mean, the reason is Korea recognized it first, they turned it into product first, and they've dominated, right? And they have 70 or 80% of the market for flat screen TVs. Now it will spread more countries. But that's an example. With science and technology, you're going faster. So you cannot wait till you see some other country has discovered something and then has developed it, and now I'm going to make it. You're too far behind the curve. You will not be able to get your industry up to speed in time. But it's also fundamentally important to have a whole spread of people. So you don't put all your money in basic research, but you do put a significant amount in basic research and applied research. CONACYT is supposedly putting a significant amount into basic research, but it has also an applied arm, right? And they should be linked together. And you know, we had an argument in the United States that the only thing that should be funded was condensed matter physics. But that was wrong, because now we have other things that we know, but it caused a big disruption when a president came in who said, well, we'll make only, you know, it's cheap to make the labs, but they're going to make all the new products, all the new electronic products. Well, that turns out not to be true. There are many new electronic products that came from other things, plus we're using photonics. So we're using lasers to transmit communications way more than we were using electronic means these days. The new generation of fiber optics that connect even people's homes now to the internet, so you can Netflix stream very fast or keep all your channels. There'll come a time when you don't broadcast TV, it's just on the internet, it's all on the optical cable. Right? And so it is clear that you need a whole portfolio. You need some basic science, you need some applied science, you need the transition and incubation to transfer the information to engineers, but incubation and innovation to start building new high-tech companies. And I say this again, they misquoted me in the paper, but the point is very interesting. In the world today, 85% of the increase in economic growth and the well-being of people comes from innovation, not from finding new resources like oil or minerals, or from bigger population. That's 15% of the growth of the economy of the world. 85% is from science to applied science to engineering and innovation. And it's just like, so the example I gave was the discovery of the electron, right? At the time when they were building the model, the computer model of the economy, there was one box for electronics and electrons and electricity and so forth. It's now 62% of the economy of the United States, at least it was. And you realize what a huge change that was in 100 years. You went from not existing at all to being more than half of the whole economy. And so the TV cameras, the satellite links, all that wouldn't exist without both the basic science and then the application of that basic science to real world problems. And the other place where it's extremely important is healthcare. Okay. So if you look and see what's going on, there are many revolutions in healthcare. There's only one time it came from health and medicine. The rest of the time it's come from other fields, mostly the physical sciences, sometimes computer, but mostly physics. New instrumentations, new ways to measure things and so forth, and allow people. We wouldn't have the possibility of DNA editing and all the other kinds of new healthcare things we have if it wasn't for the development of new devices to see what was going on inside of cells and measure the stuff and measure the tension and the strength of the foldings of protein. All these things that are basic to try and understand how a cell works. All those tools are physically well tools, starting with a microscope and on. Right? And you have to realize that that's where the change comes. But if you look, I have a curve I should pull over and talk. I have a talk about the change coming out. And if you look at the GDP, the amount spent per person on healthcare. So healthcare expenses per person versus life expectancy. It's a curve like this, right? And the United States is way off on one side. But Mexico and China, 4 years, 5 years ago, were sitting on this part of the curve. The life expectancy and the amount of money spent per person were the same. Right? China has moved up the curve. The life expectancy is going up. The European countries are way up high on the curve. And you start thinking about, do you care if Mexicans are healthy and they live a long time? How are you going to provide that service to the people, right? And the answer is, it comes from science. But all right, well, you say I'm going to buy the machines from the United States. You still have to train the technicians. You still have to train the people what's going on and what's happening. But there's going to be huge changes in gene therapy. Gene therapy is just starting to be effective. So there are new devices and new sensors. So I'm wearing, this guy tracks my heartbeat, and so you get them that also do electrocardiograms and everything else. And you need AI to interpret that data because you don't have enough doctors to interpret. You have artificial intelligence that interprets your personal healthcare data and tells you what you need to do and worry about. And you're going to sense it, but you know, in my speech, I say, in a forward-looking government and country, when a baby is born, first of all, there's prenatal health care, but when a baby is born, sensors are put on the baby to measure its heartbeat and its temperature and so on. And that should be stored in the person's personal history forever, not just being used in the hospital. But you also, from the umbilical cord, take stem cells. Blood stem cells are very easy to get. You can get a few other stem cells from the umbilical cord. And you preserve that. But from one of them, you do a DNA scan, and you, with the big data sets you'll eventually get, you can predict what diseases that person is susceptible to, if they're likely to get diabetes or arthritis or whatever it is. And from when the time comes, you monitor them. They may have, you know, if you have certain gene deficiencies, you have between a 40% and a 55% chance of getting breast cancer. But with some other people, it's a much lower percentage. You monitor them for different kinds of cancers. And if they're starting to develop that, you sense it very early. But there are some degenerative diseases like arthritis or other things you can detect when they're starting to happen by the sensors. And you can provide, you can take the frozen stem cells and differentiate them to take care of this joint or what other problem. And you can inject those genes or viruses that are designed to replace the bad genes, and you do that. And now people have already done that a number of times. You can make a knee or a hip that was bad. You can just get it to regenerate itself. Much better than doing surgery. And so that's basic science, but it also means even if you buy this stuff, you still got to understand that at a deep level. You can't just do it. It's sophisticated. You need the training. Or you're going to have all artificial intelligence doctors. You've got to train the medical staff and whatever. And so artificial intelligence will become more important. And we'll see that. But if you think about the economy, you think about the health, you think about what else is, you know, the things that you consider all well-being for Mexican citizens, all that stems from science, from basic science to applied science to innovations, and then to everyday life, right? I mean, there's hardly anyone left who's just a farmer, right? Who just goes out and does farming like they did in the old days. Everybody is working in a high-tech job. Right? You may not think so, but you have a camera and a smartphone and everything else, right? It's a high-tech job. You can't do your job without those devices. And it means you need to have a core of people who truly understand science so they can see what's coming along. And there will be certain diseases that only Mexicans get. And you need people who can study those genes, and map those genes, and understand what's going on. Well, that's something I feel strongly about. So I answered long.
Related to your interest for approaching or for support the new generations, have you worked in a project where that is trying to approach the knowledge that you get in your work as scientific. Have you worked in a project that they are trying to approach the knowledge you have had to younger students, like maybe elementary students?
So the answer is yes. As a professor, if you work in a university, you're a professor, you must teach. And you must teach at 3 levels. You must teach undergraduates and graduates, and you usually supervise theses. You know, their first original, well, not their first, but their major original research in the frontiers of science. And you must teach postdocs. It's like an apprentice thing. Just because a person has a PhD doesn't mean they know how to be a group leader and run a research group. So they're trained as students to learn physics. They learn the basics of physics. They're trained as graduate students how to do physics, and they're trained as postdocs in how to run a program, how to do projects, how to get papers written in a reasonable time, how to supervise other people, how to be prepared to go out, either be a professor or a group leader doing research. So I do those things as a matter of, it's my job. I used to say I had 2 jobs before I got the Nobel Prize, being a professor and being a researcher. And I got a 3rd job when I got the Nobel Prize because I got called on for many things. But all that goes on, and as a Nobel Prize or as a senior scientist, you often get called on to advise government or companies or things about what's going on, because even though people want applied stuff, companies realize they need to know the scientific fundamentals, and they need to know what other competitor kind of ideas or things are going to come up. And so they need, you get called upon to go to talk to companies about what new products are coming and what, if they've done this, is somebody over here going to do something else that bypasses them, and it's wasted, that they can't compete. And so even though people say they want applied only, they need that full knowledge, and they need for the university to be producing students who not only know the science, but know how to practice the science and understand it, to go out. And they hire, some go to universities, but some go to companies. Right? That's the primary technology transfer is by people. It's like you used to get all your data, you put it on a disk or a tape and carry it over to your other computer, right? That now the way we get knowledge to other places is we send students, right, that have been trained.
Do you think it does? I have some more questions.
Estamos muy en el tiempo, por eso les decía que poquitas preguntas. Vamos a. ¿De dónde viene, por favor?
Alcanzando el conocimiento.
Alcanzando el
Reaching the
conocimiento.
knowledge.
Reaching the knowledge. Okay.
Okay. Thank you, Professor Smoot. Which is the future, or what is the future in the gravitational waves in the research?
Okay. So gravitational waves are a field just at their beginning. And it's very much like the way the cosmic background was 30 years ago, or 20-some years ago. Yeah. And then we made the first discovery, and then we went on to take data for many years. Many other experiments were set up. We did the 2nd satellite and the 3rd satellite, and we probably will do a 4th satellite, we'll see. And it's getting into a more mature field, and now there are thousands of researchers in it. In gravitational waves, you just had the first discovery. There are many possible ways. Already on LIGO, because it took so long to develop, that everybody's grad students and postdoc, they stayed in the family. There were already 1,000 people working on it, but there will be many more people working on it. There'll be new detectors made. There'll be more impetus to put the laser interferometer in space. And so you can predict the next 10 years to 15 years, we'll be building newer and better detectors, and some observations going along and more discoveries. And then there will be this huge flood of data coming in, and many different objects are going on. And it's a field that will go on quite active and with some interesting and exciting results over the next 40 years. And then after that, it's hard to predict what was going to happen. because you don't know what else is going to be discovered and how exciting it will be, or whether there's another discovery about some other thing that starts drawing people's attention. But very many bright young people will be drawn to the field because of all the excitement of the last 2 years.
Okay, and last, and your message for the childhood in the humanity in the world?
For the children in the world?
Yes.
Okay, so it should be a positive message, which is they're actually, as bad as things seem, there's never been a better time to be alive and a human in the world. There are fewer wars, more people are better off. I've seen in Asia, not only their position, but 500 million people have been taken out of poverty to the middle class. That should happen in Mexico too. There's still many people who are poor, but you've seen this tremendous improvement in the standard of living. People that lived in villages and didn't have clean water, didn't have toilets, didn't have electricity. Now they're living in big cities, you know, because China's big. They're living in big cities, they have electricity, they have running water, they have big hospitals, stuff like that. That's an amazing change. And if you look around, even though there are wars going on, fewer people, fractionally fewer people are getting killed. It's just a very better time in civilization. It just doesn't seem, when you look at the leaders in the surface, that people are going in the right direction. And that we're reminded that there have been periods in civilization when it went up and it crashed down and went up and crashed down. It's not inevitable it always goes up. So you still have to be idealistic. You should have to be glad that you're born now and not some other time in history. But you have to work to make sure the world goes in the right direction. And we have plenty of people who are, you know, around the world who are pushing towards hate and towards other things. It's more important to realize that the world is becoming more of a single unit than it ever was.
¿De dónde viene
De televisión educativa, de la agencia informativa educativa.
Una pregunta, por favor. Adelante.
Do you think it's important to spread the knowledge, specifically the scientific knowledge, further than the scientific community? I mean, by making easier to understand, for example, your findings?
Right. So the answer is it's very important. In science, we've had great progress and great working because our goal is to discover something and publish it and make it available to all the other scientists. And that makes the dissemination of knowledge and the growth. If people were keeping their secrets in their countries, things would go much more slowly. We wouldn't have the world economy or the health things and things we have now. But there's the second question. Scientists are only a small fraction, like 1% of the population, 2% of the population, depending on which country you're in. But it's very important to bring the latest knowledge in science to the general public for a number of reasons. The first is to share with them the exciting new stuff that we're finding. The second is to let them understand how science works and what these discoveries mean and how they go forward and you know, what implication it is. And that's because we live in a society that's increasingly based on scientific discoveries and innovations, technical products, right? So I believe it. That's why, you know, I wrote this book.